This video is in review for our first exam, and I suggest that you put this slide or just press pause now and read exactly the steps that you go through to prove that a set G together with an operation star is a group. And you'll have at least 2 problems like this on the test. So here are steps 1 through 4, and you should put it on pause and make sure that you understand these steps. You do the same thing in every problem. But notice on number 2, when you the question of associativity of the operation, if it's regular multiplication or matrix multiplication or addition or function composition, you just write we know that operation is associative. But otherwise you have to compute, and you should expect at least one of the questions to be one where you need to verify the associative property for the operation. This problem we did in class, but we'll go through it again. The set is the set of all a plus b times the square root of 2, where a and b are rational numbers. And we should say one more thing here. Just a sec. Not both a and b are 0, because we don't want 0 to be in there, do we? It wouldn't have a multiplicative inverse. So this question should have not both a and b are 0. Okay, well, step number 1, we want to show this is a binary that if we multiply these, this is regular multiplication, that we do get another one in the set. So we have to verify that. And you could say let x and y be in W. Then x is equal to a plus b over the square root of 2, and y is equal to c plus d. But I think I'll just start it like this. A plus b times the square root of 2 times c plus d times the square root of 2. And if you multiply that out, you're going to get ac plus 2bd, that number, plus, and then you will have what? CB and AD. So AD plus BC times the square root of 2. Okay, so both A and B are not 0, so that will give this can't be 0, and this is in W. So we can say, therefore, multiplication is a binary operation on W. Step 2, well, we know that regular multiplication is associative. 3, we need an identity. Well, 1 is the multiplicative identity, and 1 is equal to 1 is equal to 1 plus 0 times the square root of 2. So this implies that 1 is in W. We have the identity. And step 4, we need to find the inverse. Well, you know these are rational numbers, so the inverse of a plus b times the square root of 2, all we have to do is show it's in W. That's the inverse. So let's rationalize the denominator. A minus b times the square root of 2 over a minus b times the square root of 2. And multiplying that out, we get, let's see, we get a over a squared minus 2b squared plus minus b over a squared minus 2b squared. Not both a and b are 0, so these are fine, and that is times the square root of 2. So not both A and B are 0, so this can't be 0. And we see that it is in this form. We can write it in this form. That's the membership rule for W. So we can say that's in W. Therefore, we have the inverse. So we can say, therefore, W is a group under regular multiplication in the rational numbers. You should recognize this notation as being the set generated by the two elements r squared and h in D4. Now, when you take all powers of r squared, all powers of h, and all products that you could make between them, you're just going to get the set. Well, you have r squared and you have h. R squared squared is the identity, h squared is the identity, and multiplying them together you get r squared h, and you know if you squared that you get the identity. And hr squared is r squared h, so this is all you have. Or let's write hr squared here, just because we are used to writing it that way. Okay, hr squared. So there's only 4 elements in this group. So to show it's a group, I wouldn't go through steps 1 through 4 before I just made a table. So we have E, R squared, H, and HR squared, E, R squared, H, and HR squared. Okay, I filled out the table so it wouldn't take so long on the video. And now you look at the table there and you say, oh, well, certainly it's a group. Step number 1, we have closure. There's no, when we multiply these elements together, we don't jump out of D4. So we have, let's just write closure, meaning that, meaning that we have a binary operation. When you multiply 2 elements of this set together, you always get another one, and you can just see it in the table here. Number 2, we know that function composition, I'll designate that with a circle, is associative. This is just a subset of D4, and we know D4 is a group and that this is an associative operation. So number 3, well, E is in there. E is in this set, r squared, the set generated by just r squared and h. And number 4, inverses are there because you see the diagonal. See in table that inverses exist in the set, in W, or in this set r squared h. Okay, so steps 1 through 4 is just, you can see them in the table. And something else that's interesting, look at this table of a 4-element group. We know it's a group all by itself. It's a group inside of the group D4. Later, we're going, in fact, the first class after the test, we'll call this a subgroup instead of a subset. Now, this is exactly the same group as you saw when you wrote out 4 groups of order 4. You made their tables, and we discussed how they were the same and how they were different. This is exactly the same group as U8. Remember, every element squared gave you the identity. We have 3 elements of order 2. We have the identity, and so we have 4 solutions to the equation x squared equals E. This is exactly the same group as U8. It's just that we've changed the names of the elements. Before we prove that the alternating group on n letters is a group inside of Sn, so An is going to be a subgroup of Sn. Before we prove that it's a group all on its own, remember, you've got to know the meanings of these words. You have to know that An is the odd permutations in Sn. An is a subset of Sn. It is the odd permutations. And we know that the order of An, how many are in there, is exactly half of the number of permutations in Sn. So the order of An is n factorial over 2. You also should know, just as a matter of fact, that if you have a permutation sigma, and of course we know in Sn we have sigma inverse, that sigma and sigma inverse are the same cycle type. In other words, if sigma is a 3-2 cycle, then so is sigma inverse. And so we're going to use these definitions and these facts that we know in proving that An is a group. So, step number 1, let's let sigma and beta be elements or permutations in An so that we know sigma and beta are even permutations. Good grief, I wrote odd there. I don't want to do this over. The even permutations. So let sigma and beta be even permutations in An, and then sigma beta is even. Because if sigma and beta are both written as a product of an even number of transpositions, then sigma beta is an even number. It's the sum of the two lengths of the products here. I could be more careful here. I could say sigma is a product of an even number of 2 cycles. Beta is a product of an even number of 2 cycles. So sigma beta is 2. Therefore, sigma beta is an element of A sub n. And we know this implies then that function composition is a binary operation on An. We knew that it's a binary operation on Sn, but we had to show closure in An. So 2, well, we already know that function composition is associative. So we don't need to talk about that. 3, the identity permutation, we have to show it lives in An. In other words, that it's an even permutation, and we can just write it as 1, 2, 1, 2. We see it's written as a product of an even number of transpositions, so this implies that the identity is an element of that set. And then 4, we need to show that inverses exist. Well, for sigma in An, sigma inverse has the same cycle type. So, if sigma is even, so is sigma inverse. Therefore, sigma inverse is in An. And we're done. Now you would draw a conclusion, therefore A sub n is a group. Okay, here's a new problem. Define the operation star on the integers by A star b is A plus b minus 1. Prove that the integers together with the operation star is a group. So in this case, we're going to have to show associativity, and we have to, of course, go through all 4 steps. So we'll start with 1. Well, the set that we're in is the integers. So it's clear that if A and B are integers, so is A star B, which is A plus B minus 1. So star is a binary operation on Z. Now, number 2, we have to be more careful than usual. We have to prove that star is associative. Okay, so I'll go A star and then in parentheses B star C. Now, this will be A star. Well, B star C is B plus C minus 1. And starring A with that, we get A plus B plus C minus 1 minus 1. So we'll have minus 2. Now let's do A star B star C. And why don't you put it on pause and see that you get exactly the same thing. We would have A plus B minus 1 star C, which is A plus B minus 1 plus C minus 1, which is A plus B plus C minus 2. Therefore, these are equal, and we say star is associative. Notice we say the operation is associative, not the, we don't say the group is, it's the operation is associative. Well, now we're going to have to find an identity for this. Clearly the identity is not going to be 0 or 1, because this isn't, star is not addition and it's not multiplication, so we have to solve for the identity. So our goal in step 3 is we must find E in Z, an integer E, such that A star E is equal to E star A is equal to A for every A in Z. So we start by let A be an element of Z. Let A be any integer. It stands for any integer. So let's just solve this. A star E equals A. So A star E would be A plus E minus 1 is equal to A, and we want to solve for E. So let's see, subtracting A from each side, oh, E is equal to 1. Well, let's check it on the other side. 1 star A, and make sure that it commutes. You could see this is a commutative operation, but let's check it anyway. 1 plus A minus 1 equals A. So yes, the identity E is equal to 1. So we found an identity in Z. Now in step 4, we're going to let A be in Z, and we are going to have to find B, let's say, in Z, such that A star B is equal to B star A is equal to the identity, which is 1. Once we find the identity, we're going to see if arbitrary elements, if all the elements of Z have inverses. So we let A be an element of Z, and now let's just solve, see if we can find B. A star B equals 1, and we're going to try to solve for B. Well, that's A plus B minus 1 is equal to 1. Or, well, B is going to see, if we add 1 to both sides, we're going to get 2 minus A, and that's an integer. So this is what our inverse is, and let's double check it. If A inverse is equal to 2 minus A, then notice that A star 2 minus A is equal to A plus 2 minus A minus 1, which is 1. And if you take 2 minus A and star A, you will also get 1. So we conclude then that that this operation star, that Z together with star, is a group. So the conclusion is, therefore, Z together with this operation, kind of a strange one, is a group. I'm not going to write out all of this problem, but one thing I don't think we did in class was show why it would not be a group if n is not prime. So let's just show that here. If n is not prime, then this is not a group. The numbers 1, 2, 3 up to n minus 1. For example, if n is 4, 1, 2, 3, the set containing 1, 2, 3, that's not U4. We have to throw out 2 because 2 has no inverse. So let's see how you could say that. If n is not prime, then this is not a group under multiplication mod n. Now if you're on a test or something and you get confused, just say, oh, what is not a prime? Oh, n equals 4. And then write it out using 4 for n, and you get an idea of what it's talking about. But in general, if n is not prime, then if n is not prime, well, let's just write, if n is not prime, then n is equal to, let's say, k times m for two numbers, k and m, exactly in that set, in this set of numbers up to n minus 1, right? If it's not prime, if you consider all the numbers 1 through 11, well, that would be when n is 12. And 12 is equal to 3 times 4. If it's not prime, it's going to be the product of two numbers in that set. And that would mean that Km is congruent to 0 mod n. And you see 0 is not in that set. So we would say that the set is not closed under multiplication. The set isn't closed under multiplication mod n. So the operation is not a binary operation. You should know the exact definition of what we mean when we say the order of an element. The order of an element A in a group is the smallest integer such that, the smallest positive integer, such that A to the n is equal to E. So this question says, what is the maximum order of an element in S6? Well, it has 6 factorial elements in it, so we're not going to go searching through the permutations that exist in that group, but let's look at the cycle types. In S6. Well, you know that we could have 6 cycles. We can have 5 cycles, 4 cycles, 3 cycles, 2 cycles. And of course we have our identity, which is a 1 cycle. So this, and now what else do we have? Well, we have 3 cycles. We would have 4 2 cycles, and let's see, what else? 4 2 cycles and 3 3 cycles. Oh, we could have 2 2 2 cycles, and we can have 2 2 cycles, and we could have 2 3 cycles, right? And I think that's all. So now let's just think, what are the orders of these? I'm going to go through. A 6 cycle has order 6. A 5 cycle has order 5. 4 cycles, 3 cycles, 2 cycles, and the identity. I'm writing the orders in yellow. A 3-3 cycle, well, each of those cycles has order 3, and the order of a permutation is the least common multiple of the orders of its disjoint cycles. Make sure you know those words so that you can remember. So the order here would be 3. The least common multiple of 4 and 2 would be, well, the order of that is 4. The order of a 2-2-2 is 2. The order of a 2-2 is 2, and the order of a 2-3 would be 6. So here we have the maximum order. And I wanted you just to go through looking at all the cycle types and remembering that the order of a permutation is the least common multiple of the cycle lengths of its disjoint cycles. Okay, so what is the maximum order of an element in S6? Well, here, let me change color here. And I will go back and circle. Let's go back in green and just circle, look at the ones that are AN. 6 cycles are odd, but 5 cycles are even. 4 cycles are odd, but 3 cycles are even. A 2 cycle is odd. The identity is even. 3-3 cycles. Well, a 3 cycle is even, so a 3-3 cycle is certainly going to be even. A 4-2 cycle. Well, a 4 cycle is odd and it's multiplied by a 2 cycle, so there will be in total an even number of 2 cycles, an even number of transpositions. 2-2-2, obviously odd. 2-2 is even, and a 2-3. Well, a 3 cycle is even, so a 3 cycle times a 2 cycle would be odd. So the green arrows are pointing to the cycle types in A6, the even permutations, and we see that the highest order there would be the 5 cycle, which has order 5. So the maximum order in A6, is 5.